Let's now run through and work out what gets created on the stack and heap as each line of our code runs. So the first line of code is going to create the list object. The new keyword in this line means find some free space on the heap large enough to store this object, and then we'll reference this new object from the local variable called myList. So I've created on screen here a box within the heap to represent the data for this object, the list, and a box on the stack called myList, which is the variable that contains the memory address of where in the heap this object lives. In Java, you can't view this address or have any access to it. Let's look now at the next line of code. This line is adding a string to our list. Now a string, of course, in Java is an object, so Java will need to create this string object. We can actually think of this line of code as being the same as this version here, where we are creating a new string with a value of 1. When we think of it this way, we can see there's a new keyword in this line, so that means Java needs to find some space on the heap large enough to store our string object. So Java will create an object on the heap of type string with a value of 1, and this will be referenced from within our list. By calling the add method, we add the reference to the string to our list object. Note that there's nothing created on the stack for this string. We don't have a local variable reference. The reference is only in the list object. If we think about the code that we can write at this point, we can't call the string object that we've created directly because we haven't given it a variable name. We can only access this string object through the list object, and that's represented by the stack and heap diagram that we can see here. In code, we can only reference the local variables that are on the stack, and the string that we've created is not directly reachable from the stack. As we progress through our code, the other string objects will be created in the same way. Note that I've put these string objects in different parts of the heap. Where the object actually resides in the heap is not visible to us as programmers, but I'm making the point that there's no reason for the objects to necessarily be close together or in any kind of logical order. We've now got objects scattered all over the heap, but ultimately we can access any of these objects through some route, which I'm representing in this picture with the arrows. As coders, we can only access the reference in the stack, but we could get to, for example, the second string object by calling mylist.get and then the item in position 1. We can call mylist because that's a variable on the stack, but we can't call anything else in this example because there are no other stack variables. Let's advance now to the line which calls the printList method. The declaration of this method is public void printlist, and then we pass into the method the list of strings and we call it data. So when we're in printlist, the stack will now look like this. A new local variable is created called data, and this variable points to the same object as the mylist variable. It's a copy of the mylist variable, and the reference for mylist is copied into data. Hopefully, it will now be a little bit clearer why using the heap for data is suddenly a much better choice than if all of this data was stored on the stack. All the JVM needs to do in order for us to be able to pass the list into another method is make a copy of a single pointer and to pass this copied pointer from one method to another. The underlying data itself, the list and all of the strings referenced into that list don't need to be copied. So that is relatively quick and inefficient. Because we're now in the printlist method, the mylist variable is out of scope. We can't access it. Let's expand the printlist method to do something a bit more interesting. So here I've got a new version of printlist, and before the first line runs, the heap and stack are just as we can see on screen here. So what would it look like, however, after this first line has run? Well, the get method of the ArrayList class is going to return a reference to the object that we want. As we're storing this in a local variable called value, this means that a new reference on our stack will be created. Now I'm using different coloured arrows in this diagram purely to make it clear which box on the stack points to which box on the heap, but there is no significance to the colours that you're seeing on screen. So note at this point that the object with the value 2 is now referenced from two different places. It's referenced in the list as the item in position 1, and it's referenced from the stack as the variable with the name value. And I hope that makes sense, because we could get to this item with a value of 2 either by simply referencing the value variable because that exists on the stack, or by doing mylist.get and then the item in position 1, or by doing data.get and then the item in position 1, because data again is a variable on the stack. Note at this point we can't do mylist.get, mylist is out of scope, this method cannot see the mylist variable. The next line of code is going to create another object on the heap, and I hope that will be quite straightforward. It'll create another object which will be referenced from our list. And then we return from the printlist method. As we're reaching a closing bracket, this means that the value and the data variables that were created within this method are going to be popped off the stack. So some of the references are also going to be lost. And also the mylist variable is now going to be back in scope. The significant thing here is that our previous method, the one that called this printlist method, is going to see our modified list. Our list now has an extra item in it, the item with a value of 4. Remember that the second method was working on a copy of the reference to the list, but not a copy of the actual list itself. The two references were pointing to the same list object. So this allowed the second method to amend the list created by the first method. Now I'm going to end the video here, and hopefully we have at this point a reasonable understanding of some of the basics of how memory works in Java. Don't worry if this still feels a bit academic, or if it doesn't all completely make sense just yet. We're going to be looking further at how the stack and heap work and how to use this knowledge to make us better programmers in the next few chapters. And once we've seen a few more examples, I promise you it will become clear, and we will have some practical use for this knowledge quite soon. In the next chapter, we're going to talk about passing objects around our code in a bit more detail, and we'll understand what this means when we say that we pass data by reference or by value.